with that name for me, and I changed my name. And, sorry about that. Great.
Andrew, if you would like to start sharing the screen, computer,
Yes,
whatever,
yes,
test
just,
everything you want.
Yeah, please share the presentation just to make sure that it's running. Okay, please, Andrew.
Should I?
And yeah, sure. Or you, yeah.
Okay.
Where was that you wanted to share?
Your presentation, if you would like to test the sharing. And also, Chong, if you want to add Med Office to close to your name.
Oh, okay. I'll do that again.
Yeah.
I can change my stuff. Oh no, what I'm doing. Okay. Rename.
Yeah.
Perfect.
Just run some slides, please. Just to see if it's yeah.
Yeah.
Okay.
There's a movie. Let's play that.
Yeah.
Does that work for you?
Yep.
Yes.
I can see it.
There's no sound, or is there sound?
There's no sound.
Okay.
Ilmar put no sound.
Okay, cool.
Thank you.
Okay.
Hi, Sabrina. Hi, Gerard.
Hi, Chiara.
Hello.
Hi, everyone.
If you want to put the name of your organization close to your name, be welcome. So just as you wish.
Oh. Can you see my screen?
Yes.
Yes, key take-home messages.
But put in
If
presentation mode, please. So
Yeah,
just,
I'll try that. Hang on. So what do you do now? Do you see the last
see
page?
The key take-home messages in
Okay,
full
so that's the last
presentation
page.
mode.
Hang on. I will do the. What about now? Is that okay?
Yes.
Can I try a little video to make sure it kind of plays? Because that one, I'll try to click on it, see if it works. Does it work for you on
Yes.
the left hand side? Okay, great.
Yeah. And there's also no sound on this one?
No,
I
no
assume.
sound.
Great.
Okay, I think that's the only click I have. Okay, great. Yeah, thank you. I will stop sharing.
Jared, do you also want to try sharing your screen?
Stop now. I'll mute it.
Do you all know each other in this team?
Really?
Maybe quick introduction. I mean, Sabrina and Andrew, you know each other, right? Yes. Okay, excellent. And I'm not so sure if Chongyan, do you know all of us? Or, I mean,
I only know you, Chiara, I think.
oh, okay. Then I do a quick round of introductions.
Can you run some slides, please, Gerard? Just to make sure it's okay. Okay, perfect. Thank you.
Great, thank you.
Okay, so quickly, Chongyang is working for GRIST. This is one of the projects that we run at DMI together with Erica. So Erica and me, we work together. And Andrew is coordinating Oceanize. This is also one of the projects that we're running. So we are helping out Andrew in coordinating. Jared is a long-time partner in several projects that we've been working together. And from Maynooth. And then we got Sabrina, and Sabrina's been partner in some of my projects, but she will be partner in project starting in January as well, OPSI for Klima. And yeah, and I think I will keep you all connected probably sooner or later in events like this, if we got the chance to present again something of this kind.
May I know just who we are expecting to come up on this meeting? What kind of public we have?
Katarina.
Yeah, Katarina.
Well, I have the lists, but I have to make the download. So at this moment, I cannot tell you who's attending, but I will try to share with you during the session. But nevertheless, we will be able to see the participants when I open the webinar, and probably recognize most of the names.
Okay. Anna, would you like to try to test the sharing of your
Okay.
screen? Because you're here and we did all the tests. So and Anna, you know Chongyang because probably you've been in contact for Greece before.
Yes.
Okay,
Mhm.
excellent. Yes, there is a connection there.
Yeah. So it's working, right?
Yes,
Yes.
excellent.
All right. Cool.
Thank you. There was one similar activity that we did with Joanna, a colleague of us, for one of the workshops last week. And it was mostly early career researchers joining this kind of workshops formats. So my expectation is we are talking to people at the beginning of their career.
Mm-hmm. Yeah, I understand.
Let's see what we get.
New blood.
So I will open the webinar, okay?
Yeah.
I'll be in the backstage.
Yeah.
Just
You need
before you do
anything?
that, could you
Yeah.
remind us of the running order, and will you give us a warning when we're getting to our 10 minutes?
It will be Erika doing this
Yeah, I
because
will
Erika
do
is
that.
moderating. Mhm.
Yes, I will do that. And then I will also, in my introduction, I will go over when people are going. And then I will also cue you as well. So
Okay.
no stress.
Should we keep our camera switched off during someone else's presentation, or?
It's better.
Okay.
Yeah.
So I'm going to open the webinar, okay? I'm going to be in the backstage. Have a great session. Erika, just when I open, just wait 1-2 minutes just to let people join us, and then you can start, okay?
Okay, for sure.
So have a nice session.
Thank you, Katarina. Thanks.
Thank you so much.
All right, hello everybody. We're just going to wait 1 minute until so we can get people into the focus session, and then we will start our focus session for today. All right, I'm sharing my screen, so I can't really see if we have a full overview of the attendees, but I think I will start our focus session now. But hello and welcome everybody to our Ocean Best Practices Workshop focus session. Before starting off, I'll just give a quick introduction of myself. I'm Erika Hayashi from the Danish Meteorological Institute, where I work as a project manager on our international projects and initiatives. And I will be kicking off this focus session as well as moderating the panel discussion and Q&A later on in the presentation. And quickly, I just want to give a thank you to the Ocean Best Practices team for helping organize this, as well as our presenters that you will meet later on for taking the time out of their day. We're happy to give an example of some activities and best practices in ocean observations. So our focus session for today is intended to be broad in nature and where we will bring a range of perspectives and expertise from our speakers to provide an overview of the importance of ocean observations, marine science collaborations, and policy implications. And altogether, we bring our speakers together to convey a coherent overview of the interconnectedness and complexity of ocean climate dynamics. So just to elaborate on some of our specific focus session objectives, we aim to highlight the important role that the ocean plays in the global and regional climate. We also seek to stress the need for measuring and observing the status of oceanic properties through showcasing the importance of satellite and in situ observations, and how these can provide key data for climate models, services, evaluating and forecasting tipping points, as well as for decision-making at national and international levels. And lastly, we will shed light on the importance of international science collaborations in informing these efforts and how we can also bridge gaps between science and decision-making for climate adaptation and mitigation strategies. Perfect. So just an overview of our focus sessions. We will have a 10-minute presentation or elevator pitch from our speakers, who will bring forward their expertise and perspectives. And then following this, we will have a panel discussion as well as the opportunity for a Q&A from the audience. And I just want to quickly introduce our speakers before we dive into the nitty-gritty of our session. So as mentioned already, our speakers are coming from a range of backgrounds and expertise, including oceanography, climate modeling, remote sensing, and spatial planning. They also represent a number of organizations, projects, and initiatives, which you can see here. And this includes some current and upcoming Horizon Europe projects, such as Ocean Ice, TIP ESMA, and OPSI for CLIM, as well as we have a Copernicus-funded open science community called the Group for High Resolution Sea Surface Temperature, or GRIST. All right, so I will just give you a brief overview of our speakers, but they will also be giving us a few words on themselves before their presentations. So we start off with our early career representative, Anna Oliveira from Plus Collab Atlantic, and who is also part of the Horizon Europe project, OPSI for CLIM, and she will present on how Earth observations are used to provide indicators that can serve to support decision-making processes for climate adaptation. Next, we have Chong Yuan Mao from the UK Met Office, and who is also part of the science community GRIST, who will present the importance of high-resolution satellite observations in addition to in situ observations. Following Chong Yuan, we have Gerard McCarthy from Maynooth University, who is also part of the upcoming OPSI for CLIM project. And he will be presenting on ocean circulation and its importance for the regional climate of Northwest Europe. Next, we have Andrew Myers from the British Antarctic Survey and also the UK grant coordinator of the Horizon Europe project, Ocean Ice. And he will be presenting on how ocean observations of the interactions between the Southern Ocean and the Antarctic's ice sheet are used to improve coupled ice sheet ocean and ice sheet climate models to reduce deep uncertainties. And lastly, on our presenters, we have my colleague Chiara Berazzotti from the Danish Meteorological Institute, and who's also part of all these previously mentioned projects, such as OPSI for CLIM, GRIST, TIP ESMA, and Ocean Ice. And she will present how research projects can provide recommendations to policymakers for informing climate adaptation and mitigation strategies. And lastly, Sabrina Spike from the École Normale Superior will also be joining the panel after the presentations, and I'll just give a quick introduction to her since she will not be introducing herself during the presentations, but will be joining the panel later on. Sabrina is a professor of physical oceanography and climate sciences at ENS in Paris. She's also one of the two co-chairs of the Ocean Observations for Physics and Climate, which is the ocean panel for the UNWMO Global Climate Observing Program, as well as for the Global Ocean Observing System and World Climate Research Programs. She also co-chairs the Ocean Observing Co-Design Program of the UN Decade of Ocean Sciences for Sustainable Development. All right, so that is your quick little overview of our focus session, and I will now hand the floor over to Anna.
Hi, good afternoon, everyone. Firstly, thank you for this invitation. It's always an honor to be together with these experts, and me specifically being someone that entered this area of research very recently. So I'm not that young, but I'm young in this domain. My background is in spatial planning, and I entered the remote sensing world through cities and sustainable cities and coastal cities in particular. So it's a pleasure to be here, and thank you for the invitation. Just briefly presenting myself, so I come from the COLAB Plus Atlantic. As with me, it's a very young institution that was created in 2020. We tackle everything related to the ocean and space technologies, but specifically climate change-driven hazards and environmental issues. We try to develop as much as possible operational models based on data science or numerical modeling techniques, but focusing on low cost and upsampling or high resolution solutions for coastal communities. And this is why I joined the COLAB, and currently I'm leading the Earth observation team as well as the technical side of space technologies. So today I'm here to present a briefly overview of what is our motivation to work on these ocean and observations for climate adaptation aspects, with some results that are not only ours, but shared in consortiums from competitive projects. And I will also briefly introduce what we see as the next steps in which we will contribute. So in terms of agenda, I tried to bring back the questions. So these are not the 5 questions, but are 4. Why we are tackling this? What are the main definitions that we built upon? How in practice we are tackling these issues and these definitions in terms of the work that Plus Atlantic is involved? And what is the future outlook in terms of where we want to go with these kind of developments? So in terms of why, what's the motivation? So this is probably
Sorry, Anna,
Oh,
are you
yep.
sharing your screen?
Not really? I should. Sorry, sorry. So I was always speed up. Thank you. And not this one, sorry. Yep. Now you should be seeing it. Are you seeing it or not?
Yes, perfect.
The full screen, right? Okay, so let me go backwards. So the presentation is valid regardless. So in terms of the agenda, I tried to bring the answer, or at least a perspective on 4 questions: the motivation, or why we are tackling these observations for climate adaptation. What are the main definitions that we take into consideration while we do this? In practice, how we are conducting these works, so mainly the research that we are involved at, and what are the foreseen results, and also some future outlook to where we want to go with this kind of analysis. And the motivation here is because we want to do something that has added value for the communities. I already mentioned the downscaling aspect. So we want something that can be operational on a daily basis and not only something for research advance. So in terms of introduction, so why Plus Atlantic and me are involved in oceanography in general and observations and climate adaptation in particular. So as it's probably common to all of you, the main driver to tackle this issue has about to the prevalence of the ocean in a global scale. We know that 70% of the global surface of the Earth is actually covered by the ocean. We also know already, it's well established, that 1/4 of the CO2 emissions that are emitted by us, by humans, are absorbed by the ocean, and the ocean has a very meaningful role in capturing this carbon. And we also know that up to 90% or more of the heat that is generated due to greenhouse effect, it's uptaken by the upper ocean and the deep ocean, but the upper ocean in particular. This means that the ecosystem equilibrium in terms of the ocean is very important, not only to activities that are conducted in the ocean context, but also coastal communities and the overall climate system. So this leads us to the energy imbalance concept. So I'm quoting here von Schumann, a very prominent researcher in this area, that states that although this is a simple number, the Earth energy imbalance is the most fundamental metric that the scientific community and public must be aware of as the measure of how well the world is doing in the task of bringing climate change under control. And they actually call for the implementation of the energy imbalance into the global stocktake based on the best available science. This is because it's not purely or not 100% understood what would be the tipping point. So there is a lot of buzzwords regarding tipping points of the ocean in terms of carbon and heat uptake and how it can generate new equilibrium systems that are outside of the weather that we are used to experience, also on land. So another quotation that I brought as well in terms of motivation is this by a EUMETSAT article referring to the same research topic. As a first glimpse, an Earth's energy imbalance value of about 87 watts per square meter may seem small. However, this value is representative for the imbalance of every square meter on Earth every second. When integrated over the entire Earth's surface, the time series of global ocean heat content change reveals an enormous energy uptake of the Earth system of about 400 terawatts since 2022. This is equivalent to about 1,000 times the power produced by all nuclear power plants in the world. But for us to achieve these numbers, these metrics, we have to have a very well-observed system, and a well-observed system both in land, in air, and the sea. And the reason why we want that is because that's the only way while we can have prospects on how our health, our food, and our lives can be affected or not in terms of climate change and extreme hazards. So some definitions. These are actually standard definitions that come from several international entities. This one in particular comes from NOAA. It's about the climate data records. And these are robust, sustainable, and scientifically sound climate records that provide trustworthy information on how, where, and what extent the land, oceans, and atmosphere and ice sheets are changing. But for us to understand change, we have to have a very accurate data record, and we have to know whenever we need to adjust to bias and errors these records so that we can draw conclusions from these measurements. To draw on this, the essential climate variables definition has been put forward by the Global Climate Observing System. And these essential climate variables are basically aspects or variables, in particular physical, chemical, or biological ones that have been observed for a long time and that can be linked to certain aspects of the Earth system, of our Earth system, to critically contribute to the characterization of the climate or how it's changing and how it impacts lives. And drawing on this, the Global Ocean Observing System also developed the essential ocean variables that help us interpret the connection between the oceans and elements such as the atmosphere, biosphere, hydrosphere, cryosphere, and anthroposphere. So basically, it's the same principle, and some variables are in common between both frameworks, but the rationale here is to have consistent measurements, long-term consistency, spatial consistency, so that we can draw conclusions. So what can we say about observations data? We do have direct measurements, and in terms of the ocean, we do have buoys, ships, Argo, autonomous vehicles, and gliders, for instance. And we also have indirect measurements such as satellite data, but also acquisitions from aircrafts or UAVs. But with our ultimate goal is to have models for inference. In terms of climate change, what we want to tackle is adaptation. But to tackle adaptation, we need high quality data. So we need to basically make data fusion techniques that are reliable between the pros and the cons across these two kinds of data acquisition methods. So in practice, how have we been doing it? I'm bringing the example of marine heat waves. So marine heat waves are persistent extreme events of anomalous warm SST, sea surface temperature, with respect to usual values. Usually the method we employ to describe this in terms of climatology is to compute the average across 30 years period, then the percentile to be used as the threshold. It can be the 90th percentile typically, but it can also be the 95 or 99. And then we check whether there is a sea surface temperature deviation from this baseline. What we find when more than at least 5 days, consecutive 5 days surpass the threshold level, is that we can state that we have a marine heat wave. And we can go a step forward and characterize these marine heat waves in terms of intensity by how much the threshold deviates from the interval between the mean and that threshold reference, so between the mean and the 90th percentile. So this multiplicative effect can state by how large a marine heat wave is compared to the climatology, and can be used to characterize extreme events of sea surface temperature globally and locally as well, and how they can possibly impact locally. So one thing that has been developed with the involvement of Plus Atlantic is the CareHeat project. It's a ESUP-funded project that tackles basically this question: what happens in a non-stationary system? Because we know that there is a positive trend in SST. So what happens to marine heat waves if we consider this trend to be the underlying trend that describes positive trends in terms of marine heat waves? And what has been done by the project is actually the computation of a novel marine heat wave atlas that has at the same time the traditional method that I just described from UpDay, but also reconstruction in 4D, and also a novel marine heat wave atlas, so let's say a second column that uses a different algorithm based upon the trend of the time series. And what we did find out, this is an example from the Mediterranean Sea, is that whenever we take the underlying signal from warning of the surface, we cease to have a positive and significant trend in terms of marine heat waves occurrence, in terms of frequency, duration, or intensity. This means that the overall positive trend that we found out in terms of marine heat waves observation is actually the byproduct of the long-term trend of SST. And this is something that was showcased and is now published in what respects to the Mediterranean Sea, but also globally in several locations. So it's not only a case specific of the Mediterranean. This does not mean that marine heat waves are not important or that they do not have impact, because living organisms can take a long time to adapt and often require special shifts of their distribution. But this does mean that the underlying effect triggering the marine heat waves is the climate change and not the extremes deviating more from what is the equilibrium state. In addition, we are also trying to establish what is the relationship between these trends and what we see in terms of climate modes in the Atlantic. And to do that, we have to basically compile what are the climate modes in the atmosphere, and especially the patterns of synoptic weather and how these correlate with marine heat waves. This is still a work in progress that is to be developed further still, but here we have an example of a negative mode in the North Atlantic, where we can see the centers of high pressure traveling further north, and you can see in response to that a marine heat wave building near the pole. By contrast, I'm showcasing here another example from 2018 of a very solid jet stream in a positive North Atlantic oscillation mode. And as you can see here, the high pressure centers are mostly in the mid-latitudes, and this leads to a buildup of heat and SST and marine heat waves in the center of the Atlantic instead of being on the poles. So this leads me to the trend. This is an example of the number of heat waves and how they have been changing over the Atlantic without the trends, so the specific results from the observations. And as you can see, you see positive trends overall in the Atlantic. But what's more interesting is when you classify... Sorry, I'm arriving at the end.
Yeah, okay, perfect. Just, yeah.
Yeah, okay, sorry. What's more interesting here is the comparison across the climate modes, the positive and the negative ones. And as you can see, for instance, in the polar region, you have more frequent heat waves in years that are in negative mode compared to the Mediterranean Sea, where you have an increase when you have positive modes, which are trend examples of the climate modes I've just showed you. And finally, almost to conclude, this is not important only for the climate system, but also in terms of specific impacts. And here is an example of how we are using this information to tackle aquaculture farmers' productivity. And we can see for a fact that when we use SST, we can improve by 60% the growth rate estimation, so the forecast of the growth rate of the fish, which leads to optimization from the farmers in terms of food stock. So just to finalize in terms of future outlook, we would say that low-cost sensors, the availability of more remote sensing data, citizen science and physics-informed artificial intelligence are key buzzwords that can lead to bridge the gap between the climate observations and the user uptake. But please bear in mind that if there is garbage in, there's also garbage out. So these kind of novel technologies are only worth it if the information we provide in terms of observations is reliable, regardless of where that come from. And to this effect, I ask you to follow on the OBSI4CLIM project that is tackling this issue to develop further ocean indicators with consistent frameworks for observation. And with this, I conclude my presentation. Thank you.
Thank you, Anna. Perfect. So next up of our speakers is Chongyuan Mao from the UK Met Office and also part of GRIST, the Group for High Resolution Sea Surface Temperature. Take it away.
Hello, everyone. I'll just introduce myself while trying to get the screen shared properly. So I'm Chongyuan Mao, work for the Met Office in the UK. So my job mainly is to look after marine observations and to for better use in the marine analysis as well as ocean models. So just a quick check. Can you see my screen now?
Yes, but you should go into presentation. Yes,
is that okay now?
perfect.
Yeah. So today I'm going to build on Anna's great overview just now to kind of draw attention probably more to the observations, in particular observations from satellite and how it benefits or complements the in-situ observations. So my slides are based on previous presentations by colleagues from UMassat, as well as some training material from colleagues in the Met Office. So first, I'd like to emphasize both in-situ and satellite observations are very important to have a better observing system. They all have their like strengths and weakness. I think this look very similar to one slide from Anna's just now. So just quickly go through. So in-situ observations are our only way to know the subsurface structure and its direct measurement. However, it's sparse in coverage. Even with Argo, we're coming to about 3,000–4,000 a day, and it's limited by weather and ocean conditions sometimes. So you might have biases towards summer, you have more observations, or you have observations more in one region, not so much in the other. And you need a lot of quality control to make sure that they are consistent historically and also with different platforms. For satellite observations, obviously you can reach global coverage very easily and provide information on large scales, and you can reach millions of observations easily a day. However, it doesn't measure the variables you're interested in directly. It's retrieved from radiation, and these radiation are affected by atmospheric processes like clouds or dust or aerosol. So yeah, they can all bring uncertainties and errors. A couple of examples of how we can sort of sense from space. We can look at the surface temperature, salinity, sea ice, surface roughness, surface height, as well as ocean colors. So these are just a handful of examples of satellites out there. There are plenty more available out there. So today's presentation, I'm going to focus on the surface temperature. For one, that's the most mature observation using satellites, and it's the ocean temperature can be used as proxies for many other ocean processes, and internally and externally it interacts with internal ocean processes as well as atmosphere. So it's very important in understanding and monitoring the climate. So as a group called GRIST, we are a bunch of scientists, and to coordinate and providing satellite global SST and also provide uncertainty for our users, so you have more confidence in using the data we provide. And particularly, we provide guidance on the data quality as well as format. So when users want to combine multiple products, they can do this easily. And we have annual meeting, which provide opportunity for everybody, from the data providers to the users, to come together and explore the SST products together. So on the right-hand side is just very simple schematic of kind of overview of how satellite works. So we have roughly two big groups of satellites. One type is geostationary, which rotates with the globe, and it only look at a specific region on the ocean or the land. And we have the polar orbiting one, which they stay stationary in the space. But so as the Earth rotates, it can reach a kind of global coverage in about 7 to 10 days. And we look at different wavelengths. Some of them look at the infrared area, which can produce very high resolution observations, but they are subject to problems from clouds cover. And we also have microwave sensors, which can see through clouds, but they have like larger footprints and low resolution. So to achieve a high resolution SST, we need really a reliable retrieval algorithm, effective cloud detection, quality control, and validation to make sure that is the best quality we can achieve. So why we want to do this? So the globe is warming, is changing the climate. On the right-hand side, I gave you an example of the global average temperature difference, and the top right panel give you a visual look at the temperature has changed, especially in the past couple of decades. The data come from the HAD Curve 5. The bottom right panel is a kind of similar story, but coming from multiple models and produced from different organizations. And they even have different initial conditions, probably different forcing. And they kind of all reach to the same conclusion into the past few decades. So something is happening. And why SST is important? Well, ocean is very important system. So understanding ocean temperature, which give an example of the definition for SST in the bottom left figure, which is given by GRIST. The SSTs influence the seasonal prediction and is affecting the regional global atmospheric circulation. It's quite often being used for the weather forecasting as a boundary condition, and internally also affect the density and circulation of the ocean, as well as affecting the living organism and the biochemical processes, as well as marine ecosystem. So it kind of affects all parts of the ocean and a very important big part system. So a couple of examples of how we use SST, especially the data achieved by remote sensing. So on the left-hand side is a clip talking about the marine heat wave, which is probably hitting the media like constantly this year. On the left-hand side is a average temperature anomaly for the North Atlantic Ocean during May and June of this year, and you can see the buildup of the marine heat wave very clearly over these 2 months, and these were very difficult to achieve a global kind of view using just in situ observations. So that's one benefit. On the right-hand side is a snapshot of the Mediterranean Sea on the 13th of July. Again, it's hard to achieve this kind of global basin scale view. Another application is in the Arctic. So on the left-hand side is a Arctic sea ice extent difference from 1981 to 2010. On the right-hand side is average surface temperature normally north of 60 degrees north of from 1982 to 2019. And you can clearly see there's some sort of negative correlation between the sea ice and the temperature. And if you notice that both the time series starting from around early 1980s, and that's basically when we start to have a operational satellite observations on both ice and temperature available to the science community. So this gives us a chance to start to understand some process which probably previously difficult to reach by in situ observations. So we can start to understand the processes in these regions. However, because the lack of in situ observations in this region, to improve observations here is still a big challenge for us. We need in situ observation to validate the satellite observations, and also due to the angle of the satellite, quite often the polar regions on the edge of the swath, which means there are lower quality, and hence you need better validation. And also these regions tend to be very cloudy, lots of water vapor and clouds, and that affects the effectiveness of infrared observations, which is what we rely on to achieve high resolution observation. So there are more need to do in the future for us to improve our observations of the ocean. Other challenges for SST, including to improve the coastal SST data quality, which similarly to polar region, is due to the observation, the water vapors, and sometimes for this case also the river runoffs could be more turbulent in the local area. So we need a high resolution satellite, maybe from multiple sources. Another challenge will be improving the SST feature resolution, and these usually be relying on the infrared, but they are affected by cloud cover. So we need more techniques to properly detect cloud cover, and especially in some particular regions, we can use other processes to work together to provide a better resolution. Here is a list of the priorities for the next decade to improve SST, as I just mentioned, and a couple of innovations that we could address that. For example, the constellation of satellite observing system, and different ways to validate the SST, for example, the fiducial reference measurements, etc. So there is a better, a kind of full summary of these kind of recommendations in the paper by Alcaro et al. From 2019. The link is in the presentation if you'd like to have a read in more details. So here I'm just going to leave my take-home message here. So just to emphasize again, since surface temperature is a very essential part of operational meteorology and oceanography, and also for the future climate prediction, and satellite SST observations complements the in situ of observations in mainly by providing good coverage and good large quantity of measurements so we can reach regions which previously impossible for us to monitor. And the main challenges are the Arctic Ocean, or polar regions, the coastal regions, as well as improved SST resolution. So we need to work together as science community and with users to make future observations better. On the right hand side is just a good example for satellite observations from Sentinel-3 SSTR. Yeah, that's all. Thank you.
Perfect. Thank you so much, Chongyuan. All right, so next up we have Gerard McCarthy. Go ahead.
Thank you, Erica. Hopefully you can see my screen. So thanks for the invite to present here today. My name is Gerard McCarthy. I work at the Irish Climate Research Unit based in Maynooth University, just west of Dublin here. So to start off with, I wanted to share this picture here. This is a picture of palm trees growing on the coast of Sligo. So Sligo is in the northwest of Ireland. It's at a latitude of 54¼ degrees north. So pretty far north by many standards, but still we have palm trees growing. If we were to go to the other side of the planet and look in the southern hemisphere, down in in the southern hemisphere, we've got South Georgia at a very similar latitude. Down here in Grytviken, we've got glaciers and we've got a very different climate. Now, there are a number of different reasons for the difference in climate between 54 degrees north and 54 degrees south. What I'd like to talk about in particular today is the AMOC. So the AMOC is the Atlantic Meridional Overturning Circulation, or sometimes known as the Gulf Stream system of currents. So it's a system of ocean currents that carries warm, shallow water northwards and returns cold, deep water back to the south. It's a mechanism of the climate system for globally redistributing heat. So, for example, I gave the example of Ireland. They're having a relatively mild climate. If we compare the climate in Dublin, or the mean temperatures in winter in Dublin, with a similar maritime climate on the Pacific coast, we've got like Seattle. We can see that Dublin is 4 degrees Celsius warmer than Seattle in winter. So the Atlantic is not just a fan-assisted storage heater, but in fact, the AMOC and the Gulf Stream system of currents is really a byword for climate change. So the AMOC is a byword for climate change because of the association, I suppose, with the idea that the AMOC can turn on and turn off as part of climatic variations. So in this figure here from Laura Jackson from a couple of years back, we can see the surface air temperature anomaly and the sea surface temperature anomaly that would occur if the AMOC were to shut down. So the climate of the whole of the Northern Hemisphere would be majorly affected. So this is a type of simulation that doesn't take account of background global warming, but just looks at the effect of temperature changes in response to a shutdown of the Atlantic overturning circulation. So the types of climate transitions that we're talking about associated with this are quite major. It's not only in temperature that we see the effect. Also, when we look at precipitation, we can see that collapse in the overturning circulation would lead to a shift in the intertropical convergence zone and a polewards shift in the mid-latitude jet, meaning that in particular our summers in northwestern Europe would be drier and our winters would be stormier. The drought in summertime could have a major impact, particularly in parts of the world, such as in Britain and Ireland, where we tend to use a lot of our water from surface water. And this can have a knock-on effect for the viability of arable farming, which is a pretty severe consequence of changes in ocean circulation. So we're particularly motivated to study the AMOC because of projections from climate models that the AMOC will weaken. In this figure here, I show the IPCC, the latest report, the sixth assessment report, AR6, reporting that it was very likely, or it is very likely, that the AMOC will decline in the 21st century. Almost regardless of the future emission scenarios in this particular instance, we can see that about a 30% weakening of the AMOC is what we can expect to occur. This projection has actually been around an awful long time, so it's been around basically all of my lifetime anyway. So this is a figure from 1985 from Bryan and Spellman, who looked at a fourfold increase in atmospheric CO2, which causes a warming sufficiently intense to produce a partial collapse of what was then known as the thermohaline circulation of the oceans. So the figure on the left actually shows a 30% weakening of the overturning circulation in response to a 1% per year CO2 increase over 100-year integration, which are actually numbers that are surprisingly consistent with the current estimates from state-of-the-art climate models. A future weakening of about 30% is something that we certainly are concerned about, but even more dramatic predictions have been made. Just this summer, a study by Ditlevsen and Ditlevsen found that the AMOC could collapse by the end of the century. So in fact, their 95% confidence interval began in 2025, which led to some media outlets reporting this as that the Gulf Stream could collapse as early as 2025, which is a headline that was wrong for two reasons. But nonetheless, this really caught the imagination of many media outlets and many people around the world and led to a lot of attention. So I've probably been going around the houses a little bit before I really talk about ocean observations. Really, I'm kind of motivating the importance of the AMOC and of ocean circulation for regional climate, and for putting it in the context of projections of weakening and predictions of predictions of collapse. And the reason I'm motivating it like this is because when we look at observations, we actually see somewhat of a different story. So there's a couple of different things that are going on. This is a compilation of different types of ocean observations. Now, many of these are paleoproxies, but up on the top, we've got in situ observations from direct mooring observations from the RAPID project. Below this, we've got satellite estimates from 2 different sources. So we can see that there's good agreement between the direct observations, instrumental reconstructions, and proxies since the 1980s. However, when you go back in time, those climate models that so confidently predict the future are not able to reproduce the past that we believe to have occurred. Now, while the majority of these paleoproxies do agree, again, we can't find the same agreement with the multi-model mean of the climate models. So this is a motivation for continuing our ocean observations to really try to validate and try to understand whether the models are simulating these processes correctly. I will say that climate models are good at very many things. So, for example, here in the green bars on the left-hand side, we have observational estimates of global mean sea level from back in the 5th assessment report, AR5. The grey envelope shows the CMIP5 projections. On the right-hand side, we've got ocean heat content. Again, the green are observations, and the grey envelope was the CMIP5 projections at the time. Now, it was an issue that these green bars were not within the grey envelope for both of these key climate parameters. However, in both instances, improvements to the observational methodologies and the, I suppose, the calibration essentially of the instrumentation meant that updated global mean sea level rise estimates and updated ocean heat content estimates fell well within the projections of the climate models. So working on and improving the observational estimates leads to improved agreement, or has led to improved agreement in these 2 key climate variables. So we look to the future and we begin to question whether or not the same might be the case for the Atlantic overturning circulation. So here we have a similar situation, such as the AR5 situation for sea level and for ocean heat content, where the green bars, the observations, are not sitting within the grey envelopes of either the CMIP5 or the CMIP6 models in this instance. So climate models are good at very many things, but they do need to be supported by observations, and work is needed to both maintain these observations and to work on those observations to understand how they fit in the picture of the emerging climate models. Thank you very much.
Perfect. Thanks so much, Gerard, and on time. So next up, we have Andrew Myers from the British Antarctic Survey. You're up.
Right. Let me share my screen. Great. I'm going to assume you can see that. Okay. So yes, I'm currently one of the co-leads of the Ocean Ice Program, which is a Horizon Europe and UKRI initiative that's aiming to look at how the interaction between the Southern Ocean, or indeed the global ocean, and the polar ice sheets, mostly Antarctica, but also Greenland, act to feed back upon one another, change the levels of ice on these polar ice sheets, and how that freshwater flux into the ocean impacts the ocean circulation and ultimately sea level and climate that we very much care about. And talking about how we need very much to improve how these coupled ice sheet climate models work, and the role for observations in actually doing that. So just to give some context, if I can move to the next slide, there we are. So on the left is some figures that have been, I think, fairly widely circulated, and most people are probably fairly familiar with them, showing the changes in mass loss over Greenland and Antarctica respectively. And you can see that in both of them, the red area is showing where there has been mass loss over the last 2 decades or so. And in Greenland, this is very much concentrated around the edges of the ice sheet where it touches the ocean. Whereas in Antarctica, there's a much more spatially irregular pattern. And we see over in West Antarctica, where you might be able to see my cursor, around the Amundsen Sea, where the dramatic amount of melting is concentrated, whereas over the larger East Antarctica, there's actually little melt, and in fact, in the center of the continent, there's some mass gain. And what's driving that is really the ocean. So the ocean, and where the relatively warmer seawater comes into contact with floating ice shelves, that drives this this melt around Antarctica, and contributes to melt. So this is obviously this land-borne sea ice contributes to sea level rise, but unfortunately, one of the big current failings in our climate models that we use to run these projections into the next century and beyond is that they don't actually have interactive ice sheets. The ice sheets are effectively cold rocks, so snow falls onto them and an equivalent amount of meltwater runs off them, but they don't actually interact with the oceans. And so on the right here, we see this graph from the IPCC Assessment Report 6, showing the future projections of sea level rise out to the end of this century under various climate forcing scenarios, with SSP 585 being a fairly strong one. But these really don't take into account the melting of either the Greenland or the Antarctic ice sheets, because they're effectively not modeled in these couple of climate models. And so in order to make an estimate of what is obviously a very important factor, effectively an expert survey was undertaken. So this is not a very rigorous numerical model like these field lines. The dashed line is effectively an expert survey. And based on that, so relatively low likelihood but high impact storylines where you have dynamic melt of these Antarctic ice sheets in response to melting driven by the ocean, you can see that the melt rates could in fact double. What's not shown on this graph was other extreme outlining seychelles where you could have up to 15 meters, so almost an order of magnitude greater than shown here, into the beyond 2100. Which is effectively the melt of the entire West Antarctic ice sheet and a dramatic collapse there. So one of these tipping point type scenarios. So, and this is not just impacting sea level rise. This possibility for feedbacks has been explored in a number of model perturbation experiments. On the left here is the change in the global surface temperature in a climate forcing scenario, so a global warming scenario, but in this instance, they've effectively simulated the melt of the Antarctic ice sheet, not actively, but basically by inferring a suspected melt rate and adding that amount of fresh water to the oceans around Antarctica. And what that actually does is it drives down the global temperature. So it's still gone up, but not by as much as it would have under a scenario without ice melt. And you see that cooling is largely associated around Antarctica. And it's probably not a huge surprise that if you dump a lot of cold ice melt into the ocean, it's going to cool things down a little. But what you don't see, and what is maybe less obvious, is that this is the change in ocean temperature at about 400 meters below the surface. And you can see around Antarctica, and particularly these areas where the ocean interacts with the ice sheet, you have a dramatic warming by up to 2 degrees. And considering the water in this area is at -1, or maybe only 1 degree, that's a very dramatic increase in the ocean available heat content. And at 400 meters, this is basically where the water comes into the base of the ice shelves. So effectively, this is showing a potential positive feedback, so an acceleration of melt. So if you add meltwater, you effectively trap relatively warmer water beneath the surface layers, and it doesn't come out into the atmosphere and rather warms the ocean, and it can accelerate that sea ice melt, ice sheet melt. So these potentials for positive feedbacks really does suggest that we need to start looking at improving our global climate models, and particularly the introduction of these coupled ice sheets into the model, so we can see those feedbacks between the climate system and the ice sheet. But there are a lot of issues with this, and probably the greatest problem is that we really have poorly constrained physical processes and feedbacks for the ice sheets themselves. So we have relatively well-refined models of the atmosphere and almost as well refined models of the ocean, but we're still in a very sort of early stage of accurately modeling the cryosphere, particularly the flow of ice sheets. And you can see this in an example here on the left. This is basically showing a range of ice sheet responses, so the change in the Antarctic ice sheet under a variety of climate forcing scenarios. So this is basically climate's forced out to 2100 by the national commitments for carbon reduction by various nations. So it's a carbon reduction scenario. And we can see here that mostly the Antarctic ice sheet contributes a little bit on the average to global sea level rise, but not dramatically. And the fact this can be negative means that in a warming world, you actually have more snow falling onto the ice sheet for potential growth rather than melt. But if you select those models in a risk-averse scenario, so you select those models with the greatest response, you actually find that you can have a very large contribution to sea level rise under these scenarios. And so obviously when you're planning flood defenses and the continuation of cities, you do want to act in a quite risk-averse scenario. But these scenarios basically include these processes that are highly uncertain. So it's what's known in the area as deep uncertainty. And that's effectively a low confidence in the mechanisms driving these basal melt rates, and even a lack of agreement across the scientific community about what these actually are, not just their values. And so things like fast and irreversible changes. So this is effectively marine ice sheet instability. And this animation shows effectively growing the ability of a model to grow and shrink an ice sheet. So the ice sheet is effectively the sort of purpley color there under a variety of different scenarios. On the bottom, you can see it basically stepping through different strengths of ice. But the main thing, I think, sort of stiffness of ice, the main thing to take away from this is where the bathymetry, so this is the rock that the ice is sitting on, it has a retrograde slope, so it actually slopes downwards towards the interior. You will never find a stable ice sheet. So these are various stable points for different stiffnesses of ice. And you can see it exists stable here, and it's stable here, but it's never stable in this retrograde point. And that's a process known as marine ice sheet instability. And it allows rapid and irreversible on sort of human timescales down these retrograde slopes. And unfortunately, large chunks of the West Antarctic ice sheet are actually on retrograde slopes. They're below sea level and they slope sort of downwards towards the interior. You can see these darker patches in the West Antarctic. So these sorts of dynamic processes that are poorly explored, poorly understood, and poorly modelled really have potentially very large impacts on our future climate. So it's very much in our interests and a very great need to explore these more closely. So as well as understanding the ice physics itself, we need to understand these boundary conditions. So we don't presently have a good understanding of the Antarctic bed topography. So this map is relatively good at low resolutions, but at the sort of high resolutions you need to understand the flow of individual glaciers, we are lacking in many areas of that good high-resolution understanding of the bed topography and its shape. The material properties of the ice and the ground underneath, so sort of the friction that exists between the base of the ice and the rock underneath is poorly constrained. You can't actually directly measure it outside of fairly unique circumstances, but must be inferred inversely through measurements of ice elevation and speed from satellite observations. And because the ocean is really driving this melt to a large extent, we need to understand that. But unfortunately, the ocean beneath the sea ice in winter and the ice shelves themselves is chronically undersampled. This is particularly the case in the wintertime, and which is actually, unfortunately, when much of this heat is thought to arrive at the boundaries of the ice sheets. And the processes at the ice-ocean interface, which is usually often underneath an ice shelf itself, are also poorly constrained by observations. They're very hard to make. You basically need to send submarines underneath the ice shelves or drill holes through them, which is very hard to do, expensive and time-consuming. But this is a key driver of that change. And there's obviously many more, but these are probably the dominant unknowns. So just very quickly, I can touch on what Ocean Ice is planning to do about this to sort of push back our boundaries of knowledge a bit further. We'll be making numbers of new observations around Antarctica, both baseline observations as well as process-based studies. We'll be sending submarines underneath these warm ice shelves where much of the melting is occurring. We'll be drilling holes through cold ice shelves, which are a sort of fenced off by the ocean circulation from this relatively warmer water, so we can understand what a cold ice shelf looks like underneath and the processes that drive that basal melting. We'll be improving models both in hindcast, so our ability to forecast our ability to project how much melt occurred over the satellite record from the Antarctic ice sheet and whereabouts that went into the ocean, and improving our ability to model important things like ice calving, so icebergs breaking off the fronts of ice shelves, and rather than just dumping that water in where they break off, actually moving around in a way that icebergs do and distributing that water, which obviously impacts the ocean circulation in different ways. And trying really to explore this concept of deep uncertainty and start putting robust constraints on those currently very large uncertainty bars of future melt, both from basal melt, surface runoff, and the contribution from iceberg calving onto future melt out to the year 2300. And finally, we'll make some of the very first first estimates of using a coupled climate model with a coupled ice sheet to look at these tipping points, so melting large chunks of the West Antarctic and seeing how that actually impacts global circulation and ultimately global climate. So, yep, please do get in touch with myself or Ruth Mottram at DMI, who's the other co-lead of Ocean Ice. And you can find us on any of these websites, any of your usual or favorite social media and at our website. So thank you very much.
Thank you, Andrew. All right, and so we have our last presenter up, Chiara.
Yeah, getting there. So let me just get this on the first and we start. So you see it right and everything is fine? Yeah?
Yes.
Okay, excellent. So I just wanted to propose a very quick exercise to all those today attending this workshop. Can you post into the chat the name of recent projects you've been working for? It could be like an international project or an initiative or a European funded project. I would be very curious to know where you have been moving around in the last few years or where you're planning to move in the next few years. My 10 minutes is a slot related to a very specific topic. I'm not a scientist. I'm actually a project manager like Erika. I have a background in economics and I specialized over the years in supporting a number of research projects in trying to provide results to a number of audiences and provide recommendations basically to policymakers for informing climate adaptation and mitigation strategies, mostly in Europe. So the idea was to present you very quickly some lessons that we learned across different projects, because normally projects gravitate around the same initiatives and they work as well for the same audiences. And there are some, let's say, lessons that we learned, a bad way, in a good way. And this is what I wanted to share with you in a couple of minutes. But first of all, the idea was to understand what's the point in engaging at all. Then to walk you through some examples of storylines for specific audiences and try to put you in the loop in topics related to science, to policy initiatives, so science for policy initiatives that you might try to connect to in your life. And how to work with media could be a nice chance, but you need to be aware of something. So we did also here some nice experiences and bad ones. And also how to connect to specific partners that I call intermediaries, because they're basically able to bridge science to policy in specific projects from within. And one of these intermediaries mostly that I've bumped across are basically actors from the social sciences and humanities, and why it's very important to integrate them fully in the projects, in the research projects that you're running. But when we're talking about these topics, I know that for scientists it's difficult. I've been working in this kind of area for the last 20 years, so I understand your comfort zone is there, and probably at the moment you think, well, I'm here and I'm not really comfortable when we're talking about policy, engaging with policymakers. Can we do it? How could we do it in practice? So the idea is to understand why you should do it at all. Science is able to provide a number of data. We were talking about satellite data, observations data in these entire talks in different parts of the globe. But we're also talking about economic data, because climate is also partly affecting our economy. Socio-ecological data. So all these kind of data, they could be used at some point by those taking decisions. And it could be like local governments, national ones, international organizations. So the decision block in the yellow part is where basically decisions are taken for global response to an emergency, like the climate emergency, but also to adapt, to mitigate some of the effects, to create development that is a sustainable one, dealing with resource planning, management of resources, management of health, for instance, well-being and transition, just transition. And in between, most of these projects have been actually testing a number of formats in the past years. Some of them a bit more successfully than others, but at least you got a list, yeah. So I think one of the main tools, and this is what I wanted to address in a couple of slides, is the tool of the storylines, of the narratives that need to be developed by each project. So there isn't a way to escape that. Then you can try to add other formats, for instance, foresight, pictures of the futures, creating scenarios, providing recommendations, going into co-production, co-design of information together with those taking up your data, elaborating on interdisciplinary collaborations, activating participatory processes like citizen science and so on. So let's go through some of these. The context is very complex at the moment, so we're talking about mostly climate research here, and most of you are already familiar with these kind of reports. So, but these reports are written normally by senior people, so it might be difficult for somebody at the early career, the early career stage, to be able to contribute to these kind of reports, even with some indirect flow. But there are some other ways to do this kind of contribution, because they're all sitting on a wealth of data and information. So this is how you can bring this up at some point. Storylines. Basically, most of the research projects that I've been following in the past have been creating a number of narratives. For example, one that we use in several projects, also with Gerard here, was related to long-term sustained observations required for improved climate predictions, developing a digital twin of the ocean and of the Earth system, and then observation can help predicting some information and can help also information to be downscaled at regional and local scales for supporting climate change adaptation and prepare for instance extreme events. So this is a typical example of a storyline that you could develop. If you're working in another field, could be also related to biodiversity. I was not in this kind of project, so this is why I'm talking about these specific storylines. One specific storyline that we use along these building blocks, I call them, Atlantic observations, modeling, fish forecast, economic and societal impacts, was a briefing that we did 5 years ago in 2018 at the European Parliament in front of two members of the European Parliament, Ms. Meissner and Mr. Serrao Santos, from two different countries, Germany and Portugal. And my colleague decided to bring up the slowing of the Gulf Stream, of course, but also one specific and powerful image that a person from Germany and a person from Portugal could immediately identify, the cod. So I'm coming from Italy. My grandmother was from Sicily. She has been cooking cod all the time during her lifetime. And my other grandmother was from the north, and she was also cooking cod in her lifetime. Different recipes, but also people in Bergen, like my colleague Tore Eldevik, who brought up this kind of image, he was also eating cod. So cod is uniting somehow, you know, the destiny of the economy in Europe, and it's also linked to the fact of the slowing of the Gulf Stream, or maybe not. So this is like a powerful narrative that we brought up in a specific briefing. And it worked very well, I must say. So everybody was happy to get new data at that time and understanding what we were informing them and how they could base their action upon. Another storyline, this was a few years later, 2020, another briefing, European Parliament, two other MEPs, Michel de Mose from Denmark, and Mr. Urmas Paet from Estonia. And the storylines in this case went into different directions. One storyline was related to building block observations from the ocean, tipping points, regional local scales, what's happening for to the shipping routes on the Arctic in case of extreme events. So how can we build a block from observations to forecasting extreme events? And this was something that DNV in one project, Blue Action, brought up and created a sort of simulation a system that could predict these kind of extreme events. The second storyline was related instead to climate change adaptation, and was mostly going from observation to tipping points to regional and local scales in the direction of health system planning, urban planning, heat stress, and urban heat effect. And this was something that we developed in previous projects. The first one was under the Framework Program 7 called NACLIM, and then we brought this up again under a second project, the Blue Action, also with the collaboration of the European Climate Research Alliance. So different stories, different projects, but also very useful to the people that were actually facing these kind of problems. So Payet from Estonia, looking at the Arctic, also security issues. And on the other side, Michel de Mose with Denmark increasing the heat during the summer, and what can we do against this? So another point that I would like to address about the storylines is related to the fact that we have a number of science to policy or science for policy initiatives that are also funded by European money. So European Commission has been funding a project that was called Anchor for almost 3-4 years. It was a coordination and support action that was basically putting together different actors across the Atlantic, governments basically, and to set up a number of agreements, but also set up a number of collaborations between scientists and policymakers. And it was born, this kind of initiative, from the Galway Statement in 2013, the Belen Statement in 2017, and then the South-South Framework in 2017 as well. So basically, this project started with a little bit of money, not much, but it brought together several players around topics such as climate variability, emerging pollutants, ocean observations, and it was open to communities across the Atlantic. So you could find partners from one side to the other side, north to south. And the idea was to create some cooperative research for a societal benefit along the Atlantic from north to south. So this initiative is not active any longer, but there are still a number of initiatives connected to this kind of large movement that they created. And the scheme on the right side here that you can see is still taken from the website, and it was taken a few days ago. So it's still active, and you can still join these kind of initiatives. One example of an international initiative where politicians and also scientists, they come together. Another thing that when you are addressing your different audiences, it's not just about the storyline and the audience that is receiving the message, but it's also how to structure the message. So one interesting thing that we did in one project, we realized that not everybody was comfortable in talking to the media. So one fantastic colleague, former journalist, Ewan Patterson from the Scottish Association for Marine Science, decided to hold the training to mostly early career scientists, but there were also senior ones in the group, on how journalists basically they destructure your story and they restructure it according to what they can put together for a magazine, a newspaper, or the TV. And this training is still available, so there is a link on the slides. You can actually still follow this. It's 1 hour short training workshop that he gave. And it was extremely useful also to understand how the news are digesting information that comes up maybe from a paper, and how you need to kind of shape up your story so that it can be digested in the best way for the people to reconnect to you and to your results. And then we had also some very viral situations to manage. For instance, my former boss, Stefan Olsen, also at the Danish Meteorological Institute, at some point when he was on field work in Greenland, took this picture. And then he had to manage for several months what kind of, let's say, chaos such viral photo could create in his life, but also in our life, because the comm team was involved. But it was something that went viral overnight. So at some point we started seeing tweeting activities around this picture with requests coming from all over the world to use this picture. I guess you've seen it before, but this is where my recommendation would be to you: never try to do this alone, never try to manage the situation alone, try to get a comm team on board as soon as you can, and try to find some people that could filter for you, because Stefan could not concentrate on science any longer for 3 months of his life. So this is an interesting thing because the picture was actually used in different contexts as well to show climate emergency, water melting, dogs on the ice and so on. But I think it's an interesting point, like, are you sure you want to put this in the media? And if you want to do it in the media, do you have a backup, somebody helping you out? Think about this. One of the last points that I would like to address is about the interdisciplinarity of the teams. And this is something that has been a steeping curve also for me and for a number of colleagues in the current teams to learn. Not everybody 10 or 15 years ago was ready to collaborate with, for instance, experts in law, policy, diplomats, but also public health experts. This has become quite normal now, but the terrain has been changing the last 15 years. So this one was, again, one policy event that we had at one major conference of this All Atlantic initiative, where we brought together a number of teams from different European funded projects. You see all the logos here. And we had basically a collaboration on discussing, again, building blocks around one topic, observations, Atlantic, and so on. But I think it was something interesting that it was the first time that we had also people coming from diplomacy into this kind of working groups. And this is because science diplomacy is something that is growing at the moment. So I don't know if you've been seeing this activity before, but I would like to point here at the work of two excellent scientists and one diplomat in the team, Marie-Louise and André Polejac, and they have been collaborating on Mission Atlantic as a partner. Mission Atlantic is also a European funded project, by bringing in the concept and the methodology of ocean science diplomacy in the teams, in the research teams. Like here, you can understand it's a bit of a picture, understanding what kind of examples can be taken in international decisions that require ocean science. And we go here from fish stocks management to ocean biodiversity to, again, sargassum bloom. So there are different areas where you can have science in diplomacy, diplomacy for science, and science for diplomacy. And I have been writing a number of papers on this that are quite interesting. And this is like something that most of the projects, in my opinion, still need to learn. So this is something that you should definitely keep an eye upon in the next few years. Last slide, when we're talking about interdisciplinarity, I was mentioning diplomats, but this is not the only way to go. For instance, we try to collaborate as well with musicians in an oceanography project. So we involved one composer, Michael Begg, who was actually composing normal music also for orchestra. And we put him in contact with a number of scientists to understand how he could work with ocean data. And basically, the outcome was an album, but also a booklet where basically he tried to explain how data from the oceans with changes, with texture, with balancing could actually be turned into music. And this was something that we use for reaching out to broader audiences and also to involve at some point the general public in the kind of activity that we were already setting up. So this could be an example. I know Anna has been also involved in other examples where they use the marine heat waves to create videos, composing music, having an AI involved, and also creating poetry. So this could be other examples that we can put also in the chat later. I just would like to give you one final message. So there is no way we could have done this kind of activities and learn our lessons without teaming up with a number of similar projects on potential joint common topics. So these are 4 activities that I have at the moment on my plate and on Erica's as well. We got 2 projects that are coming up, the first 2 that I mentioned, TPESM and OPCI4CLIM, they will be starting next year, but we're still interested in opening up for collaborations in terms of joint events, joint activities, and joint engagement. And the other 2 projects that are already running are OceanEyes. So Andrew was mentioning this already. and GRIST as well. So Chongyang was mentioning this already, and we would be very welcome. We would be very happy to welcome you and your inputs if you would like to work on common activities. You can reach out to me. That's my email address. And I would like to thank a lot here, a number of projects that I mentioned in all this PowerPoint. So this you can see whatever kind of input I got from all my colleagues in similar positions. But the question that I would like to put on the table is, where are you going to be heading next? Thank you.
Thank you, Chiara. All right. So the presentations are now over and the panel discussion and Q&A from the audience is now open. So if panelists would like to turn on their cameras. And for the audience, the attendees, please feel welcome to ask your questions in the Q&A function next to the chat button on the bottom bar of the Zoom. And we will go through them and hopefully get some interesting questions out from you to our panelists. Yeah, just to start things off, going from Chiara's presentation on the where she touched upon collaboration across projects as well as across disciplines, we also heard from a diversity of speakers today who have all mentioned activities and best practices involved with ocean observations. And I just wanted to draw in one of our panelists, Sabrina Spike, just to perhaps maybe elaborate on marine science collaborations and how perhaps this can inform climate research in other geographies and implement these practices in reality. I don't know if you also want to say something about that.
Yeah, sure. So just briefly, I'm old enough to have seen all the evolution of our science, ocean science, in physics, but also in other disciplines, and climate science. So I think it evolved very rapidly, and even if the ocean actually came up in terms of awareness of being important for climate, it has been the collaboration, and Europe has been instrumental in that, have been really building through all these kind of projects that we have seen that started maybe in the 90s, to foster collaboration that were initially very disciplinary, and now they are cross-disciplinary. Probably they are not touching yet hard science or the science of the Earth system and science policy, etc. But they will start probably soon, and they bring together so different countries and scientists, and as the ocean observing system actually is run a little bit globally, and they bring in so the European scientists into this global observing system, and actually the coordination that stem from this kind of project have been able to really put together some observing systems that are still running, funded by science, but they are really meaningful for all what we have heard in terms of Earth system models, but also any other kind of projections and predictions. So like weather forecasts are really relying very much in ocean observations. So and even in terms of extremes now that really needs shorter time scales, these ocean observations are really fundamental, and also the knowledge that they come from. And I must say that different forecast centers in Europe are starting to do forecasts also with machine learning, and they are based on observations. So really observations are fundamental for decision making. So I don't know if it's okay.
That's great. Thanks so much, Sabrina. And the audience is a little quiet, but just feel free to ask your questions. But I will go over to Anna. Maybe I can ask you a question regarding more of the long-term ocean observations, and how critical are comprehensive and long-term ocean observations for accurately quantifying the ocean's role in global climate change, and what are the potential consequences of inadequate data in this regard?
Thank you so much, Erica. So I think Sabrina actually addressed this issue quite well. As I said in the presentation, I think we can all agree on that. Machine learning, artificial intelligence is a very strong trend right now. We have seen quite striking developments even in weather forecasts. And as Sabrina mentioned, the ECMWF has just released the IFS system based on AI instead of the deterministic physics, but the quality of the outputs is only as good as the quality of the inputs. So especially if we are considering climate prospects and scenarios, we know for a fact that scenarios have lower precision. They are not forecasts per se, but the better the observation data that we put in, the better the prognostics in terms of the accuracy that we can draw and the conclusions that we can draw. Because if the precision of the input is smaller than the noise of the data, let's say if the signal to noise ratio is unfavorable, then we may come out with decisions and policy indicators, etc., and engage the society in a certain aspect that is actually the noise of the data and not the signal that we want to detect and that we want to provide prospects in. So I would say, and coming from satellite data and from other applications, that the amount of data that we have now is really striking, and now the challenge is more about handling and processing it, but the accuracy of that data, detecting the inhomogeneities and everything else is of utmost importance to make sure that wherever we do with it is accurate, is precise as much as is possible to be, and provides a signal that is actually a signal and a comprehensive and meaningful one for the society.
Yes, Andrew would like to react.
Yeah, I'd like to jump in on that that point with you were pointing out the abundance of data. And I'd also have a counterpoint there that in the Southern Ocean, we have a real dearth of data in the wintertime from ships, which is our traditional platform, our gold standard for sort of all properties, and a massive lack of observations underneath the sea ice and underneath ice shelves. And those, as I spoke about in my presentation, are really critical for understanding those ice sheet ocean interactions and for really dictating future sea level rise. And so I think we find that our global observing systems, so things like the Argo program in the oceans, have done wonderful things for our understanding, but they are not at present suitable for understanding what's going on in these ice-covered regions. And they're also really only just at the edge of suitability for things like the carbonate system parameters, so understanding the absorption of carbon and carbonate chemistry within the ocean. And for that, you really need chips or more advanced sensors. So I think there really does need to be a technological push at the moment to start getting those under ice observations. And we know how it could be done, but it does require significant investment and sort of multinational collaborations. So I think there are efforts underway to start that, but I think there is quite a lot of work that needs to be done and money invested, unfortunately, in building a proper observing system that will be sufficient to start constraining our understanding of these ice sheets and ocean interactions.
There is actually a question on this a bit in the Q&A by
Yes.
Matt. So Matt is asking, is data sharing across groups, organization a barrier for any of you? Are these central repositories for data that you have found useful? So maybe we can kind of open this box.
Maybe I can start. So actually in climate and in the ocean, data sharing is really coming up like open access. So we are really working in releasing the data in new when it is possible. And of course, there is some delayed time for validation and calibration for the scientific use of the data, but data have been used in weather or ocean forecasts really from now a few years. The problem is perhaps the repository, because we have many data that stays in different repositories, so the finding of this data may be still complex, and so this is what we are trying to improve, but we have limited resources, and this is one of the recommendations of the Global Climate Observing System implementation plan that came out last year, is really to work on the data conservations and really the F part, so findable part of the data.
Yeah, hi. I can also add on to that because yeah, so I think for our observations, most SSTs, there are open resources, so anyone can register and just download. And also, in particular, we as a GRIS group, we have a ensemble of the L4 products called GIMPE, GMPE, and that's like collaboration between many organizations to come up with an ensemble of all these products to give it hopefully a better estimate of the SST fields. And also I think within GRIS, we're actually more and more talking about the lots of data storage coming to clouds. So that's actually an opportunity, possibly also risk in terms of sharing between regions, between organizations. So, and at least for SST, we have been trying for many years to create a central data catalog with the idea to provide a kind of one-stop shop for the users to find the best products for you, particularly applications, because we understand that across the globe, lots of organizations produce very similar products, and what's the best for our particular application. So yeah, so we're trying to work on that, and then I guess as scientists, we're usually trying to break down the barriers for sharing with the mind to like safety, sort of security in mind as well. But yeah, hopefully in the future we're going to be more available for sharing, I guess. That's the aim.
And if I could just make a comment there as well, I think we're lucky in the ocean community that, say, some of these large projects, such as Andrew mentioned, the Argo project, that it from the start was an open access to data straight away. And I think that's where we're quite good at, you know, from what Jung Yang said about the GRIS data, that these data sets, these large data sets, are all open. And the problem probably arises really when you're talking about individual kind of more kind of discombobulated type observing efforts. So I could give the example of observing the Atlantic overturning circulation, where it's a system of different individual arrays and nations observing it, with not a clear kind of place to deposit the data. So I think it depends on which kind of element you're looking at in terms of how open and available data sets are. There certainly is some work still to be done on that front.
Maybe I can also add something. I mean, I saw also the evolution in the last 10, 15 years on data management in these kind of European funded projects. And now it's basically the standard that you need to open up your data, make them available, make them reusable. So there are some guidelines that you probably have seen before. One is about the FAIR data. The other one is related to the INSPIRE protocols for data. And most of the obligations now, they point at making data available as soon as you publish something with this data. So making sure that data have a DOI, they are publicly accessible as soon as your publication is out. So this, I think we are going into more transparency than before. I remember still people sitting on the data and trying to, you know, publish their own papers with their own data. But this is like history long back. So this is just, it's evolving. So that's good to know. Yeah, Gerard is laughing. I know why.
Perfect. Thanks a lot for your answers. I also just wanted to piggyback off of this because since we're talking a lot about data sets, sharing data with making it open source or open access, sorry. How do you actually translate the data that we have into useful materials for policymakers? I think that's something that's, bridging that gap between science, as Chiara was mentioning, to actual decision making. Does anyone want to react on that?
I can try to address that. So we have been working with some stakeholders, mostly related to aquaculture.
Can you speak up a little bit, Anna?
Sorry? Yeah,
Yeah.
now it's better?
Better, yes.
Yeah. So we have been discussing these issues with the aquaculture farmers, and actually it has been a very learning experience in the sense that they are not climate educated. So one of the first steps to disclose, for instance, with them the marine heat waves impacts on their activities is to actually make them understand what a marine heat wave is, because the often misconception is that, okay, marine heat wave is when we have summer and it's very warm and everything is warm. But here in the Atlantic coast, as in Portugal, the water is not that warm. It's 20 degrees the most, and it's not as warm as in the Mediterranean. We have upwelling in the summer. And for them, it's like, okay, so I'm raising sea bream. Sea bream actually likes warmer waters when they are in the later stages of growth. So the warmer the water, the better. The problem is that marine heat waves are not only when waters are warm in the summer, is also when you have an anomaly in winter. And this is like the spawning season when they have the juveniles on the water, etc. And this may lead to few oxygen in the water, and the fish eat less. So there is a trade-off between the amount of oxygen available and the hunger of the fish to eat more and to grow. So it's a complex issue and not as simple as, okay, marine heat waves is warm water and it's good and the fish grows faster. And this has to do with preconceptions that the user has, and sometimes we have to listen to them to deconstruct these ideas that they have, these preconceptions that are not climate literacy, basically to provide climate literacy to them. What is the concept? What is the implications? Also some understanding of the scientific underlying aspects between, for instance, the biological response of the fish in relationship to climate, because sometimes they are not that well aware of the consequences. And so before doing something that they can take, they have to learn, understand, and we have to have a common dialogue and make sure that we are understanding each other. So I would say that's like the first step.
I would strongly agree with what Anna says there as well. And I think from our experience, the first thing to do is to sit down and talk with your stakeholders, to not preconceive of what information is useful to them. I would echo Anna's point about the need to explain, all the steps through climate change. And I think in particular, people have quite a general view of climate change, and potentially they've seen figures of something like global mean sea level rise or global mean temperature rise, and have this broad generalized kind of impression of it. And when it comes down to what actually might matter to them, so for example, sea level vulnerability in a specific port or a specific aquaculture farm, that these indicators need to be translated and that there is a job there to be done. And it's one of the things that we will address in OBSI for CLIM, is to really address those kind of bespoke climate indicators for specific stakeholders and for specific areas.
Thanks, Gerard. Sabrina, you would like to add something?
Yes, I would like to add from a more global view. So the Global Ocean Observing System, the Global Climate Observing System, they are working also with operational services that are kind of intermediate stakeholders, and they touch really with also the final stakeholders, including policy makers in Europe, etc. So I encourage also us scientists, and not just to talk among scientists, and redo the work that has been already initiated by other colleagues, and also take in what are their experience in that sense. And also the Ocean Observing Co-Design is is this program of the UN Decade that try really to look to the observing system that are trying to respond to some requirements and how we can evaluate and reevaluate it in time, this kind of observing system. So this is also something, a kind of process that need to be understood by scientists, because it is based on the framework of ocean observing system and also on the rolling review of requirements that has been initiated by WMO, but is now also pushed in terms of the ocean assessment of the observing system.
Right, thanks, Sabrina. I also was just curious then to bring this question or this discussion back to Chiara, because you were talking a lot about this, that scientists should also broaden their groups of people who they're talking to. And I'm just wondering your take on all of this. Should scientists perhaps have specific coaching on some communication methods, or also understanding or being able to speak across disciplines as well?
I think it would be very useful to have it probably with some people specialized in media communication, journalists, in their own organization. So if you see any of this training in your schedule from your employer or the university, just go for it, because it's very helpful. And in any case, we try to put some patches in some of the projects by organizing this kind of internal training for some of the people. But I think it was really interesting for people to understand and to see how some words can be misunderstood from the public, and how these words have a specific meaning in science, but they mean to the public something completely different. For instance, uncertainties. What I would understand as, or my mom would understand is that she's not sure if she says this is uncertain, but the specific meaning in science is completely different. So this kind of translation of terms is something that we needed, for instance, in also the papers that we brought up at some point. Like position papers, there was something also related to fish forecasting. I'll put this link also into the chat. And we worked on specific position papers in several loops. So there was a first draft by scientists, and then there was a second draft by people in communication, and then another draft by the scientists. So we tried to clean up whatever could create uncertainty, is the way I see it, and in a way to clean up the language so that people can get the message without being confused by different words. But it's, I think having this kind of training before you start your career or you're at early stage, that would be extremely helpful. And then also for people in my level, this is also extremely helpful to understand how I can help you out. So that, yeah, for sure. Mm-hmm. Yeah, we're going to plan to share this recording, yes. And also we will put all the different resources on a slide. So don't worry about this. If you're missing the chat, we will find a way to share this with you.
Yeah, and I think that's a really good point, Chiara, also because we're coming from sort of different backgrounds. I'm also not like a wet scientist. I'm a human geographer. So half the time I've just started working at DMI, and it's really interesting to get into these conversations and try to make sense of the words that are coming at me. And since I also work a lot with the communication and dissemination of, for example, the Ocean Ice Project, as well as GRIST activities, I have to take this information that could be complex, and it is complex, and translate it over to to different audiences who may not have that background in science.
By the way, we did an internal training at DMI on also engaging with policymakers, and this was provided by an Horizon-funded project that is called Engage 2020. They created a sort of manual on different formats for engaging with different audiences. And it's a dynamic thing. So basically you can try to understand what kind of audience you want to talk to, what kind of level of formality, in which stage of your activity research. Are you at the beginning? Are you planning the project? Or are you delivering results? And they were creating this kind of manual of formats that could be looked up. It was a fantastic project. So we got the trainers from them and we put them into the situation of talking to scientists and training scientists on how to work with these formats. It was really interesting. The material is available, so you can grab it and you can download it. I would highly recommend it.
That's great. Thanks a lot, Chiara. Does anyone in the panel have any questions for anyone else?
I think I'm just going to probably building on what we discussed from our point. I think it is very good that we have like Kira and yourself, Erica, to can do the project management. I've noticed that GRIST effectiveness has improved ever since you joined, because in the past we always thought like, oh, organizing the meeting, it's not that difficult, so it's usually a scientist double as the project management, and it's very stretched their attention and their energy. So there's no I'm not trying to criticizing anyone, not on their fault, but I think it's just not the best practice. So I think we have people who from different backgrounds and then have their specialty and then work together is really the best way forward. So I'm really impressed with how the GRIST has been transformed in the past few years. So thank you very much for that.
Thank you. Yeah, I think it's a profession that is growing because we are basically working at the interface as well. So on one side we got you, on one side we got the audiences, the stakeholders. So this is also a learning curve for all of us. So that's good to know that something is working. Yeah. But I have one question related to, your background, all of you, because did you do this formal training, for instance, on in your organizations on policy engagement? Did you have any formal activity as training on this, Andrew? No.
In my
on the job.
On the job.
in my institution, they offer training every year. Because we are a climate, not at École Normale, but the Institute for Climate, because we are very much in contact with the media. So they ask us to take it.
And one thing,
I think,
sorry. No, go ahead.
I was just going to say, for I think in the Met Office, I think some teams are more customer or media facing, so they probably have regular trainings, and other teams probably are not expected to actually go out, talk to the media very often. I think my manager probably be interviewed by a journalist like once in the past 15 years he worked there or something. But we do have training for project management and outreach training, but I think it was just if you are thinking about moving in that direction, or say you decide to work in the climate mitigation team, which means you might, it's like your job moved and then you probably would need that kind of skills, and so I think you can sign up for that kind of thing. Yeah.
And the second question, if you had any kind of situation that was difficult for you to face because maybe you had one project with findings and results bringing up certain novel ideas, and instead your institution was trying to hold you back, or maybe they were not ready to share information that was coming up from a project only. So is this like something that you have experienced? So having a sort of conflict of interest in terms of what to disclose in terms of a team in a project that is just, a layer in your life, and on the other side, what is your employer official position with some specific topics? I would be interested because that's my next challenge to learn from you. I've
never been in this.
Yeah, me neither, but I would say that there is like a pressure nowadays. It's not as much about the boss or the top level of the institution, but from society and the scientific funding agencies in particular about carbon. So this kind of carbon tunnel vision is putting a very big pressure, and the market-driven approach to carbon is sometimes and in some aspects very contradictory to what science would demand in terms of investment to do proper work. And these two things, so the market pool in terms of monetization versus the reliability and accuracy, they kind of exclude each other. Fortunately, I did not struggle with it, but I'm seeing, or I'm in the midst of the tensions.
Okay, thank you.
And I would say just it's a slightly different point, but sometimes I think media and sometimes even policy organizations come with a predefined kind of set of ideas and almost want you to reinforce their opinions or their perspectives on it, and are almost looking for a scientific validation for that. And I think it's quite a skill to, I suppose, be careful with your message so that you're communicating it effectively, so that it can be understood without oversimplifying to the point of your message becoming inaccurate. I think that's a real skill in terms of kind of trying to navigate around that.
Yeah, this was an example. There was in one of these trainings that we offered within one of the projects. There was one representative of the German Marine Research Consortium, and he actually mentioned this kind of how to pay attention in which context you are talking to and to whom. And if you are, let's say, if you are providing evidence to what they have in their mind already, or if it is something that, you know, you might be on the opposite side. So this is like, there is no solution for that is fitting every context. So you need to try to understand who your audience is and what the goal of the discussion is, to try to see if you fit or not, and if not, just walk away. That's the point. So you do not have to adjust, and that's a situation. Okay, thanks.
That's great. Thanks a lot for all the discussion. If there is no other questions from the audience, does anyone else in the panel have anything else to ask each other or would like to discuss or bring up? Otherwise, we have had a very fruitful discussion. Thanks so much for everyone for attending, the attendees, but also the panelists or the speakers who have given their time for today. Thanks a lot, and thanks to the Ocean Best Practices team for organizing all of this and hosting our focus session here today.
Thank you, everybody.
To you.
Bye.
Thank you
Thank you.
To
Bye.
you as well. Bye-bye.
Bye-bye.
Bye.